Hello and welcome to my video concerning the standard normal distribution. And in this video I'm just going to actually kind of run through an example of a situation in which you might want to use the standard normal distribution to determine some probabilities or even some percentages if you needed to do that, excuse me. But yeah, let's just do an example problem. And actually you can see I've got one right over here. So I'll read through this with you, but it says, as a mental exercise, let us consider that the SAT verbal average could be 500 and have a standard deviation of 110 points. It says find the probability that a randomly chosen individual will get a score that is greater than 700, because that would be awesome, right? That would make your day. Or B, that a randomly chosen individual will receive between a 550 and a 650, which of course are above average, and which any student that they take the SAT, that would be an acceptable score. We'll see here in a minute. But one thing going into this is I want us to assume, as we do this here, that these variables here, such as a score on the SAT, are approximately normally distributed. So let's go ahead and start by discussing what we mean by this. Recall that a normal distribution, oops, see if I can get around this here. Oh, there we go. A normal distribution is basically any distribution that's approximately what you typically say is bell-shaped, okay? And so this bell-shaped distribution, we say these are x values. We're going to convert this here in a second, but why don't we switch colors so we can see this a little bit better. I like blue, so we'll go with that. Kind of a darker blue. Hopefully we can see this. And you'll have to forgive me. I'm not very good at drawing this every time. But essentially, basically, recall that a normal distribution has its average perfectly here in the middle, which is also the mean, or the median and the mode. And we typically, go out 3 standard deviations each way from this mean. But things tend to occur, of course, more in here towards the average. And as you deviate from the average, of course, things fall off pretty quickly. So we can safely assume that, if this is our population data, we'd perfectly have some normal distribution, and we could definitely technically say that in the middle here, since our average in this is 500, we could say this is our average of 500 for this situation. And we use the Greek letter mu. Kind of looks like a U with an arm in front. I always kind of look at it as an M, but you say mu. But anyways, we're going to deviate 3 standard deviations to the right. So I like to draw on these lines because I find them helpful. But let's add 110 each time onto this. So this would be 610. See, I'm thinking 110. I wrote 110. 610, okay, 2 standard deviations above. This would be, of course, 720 if you add another 110 to the last one. And 3 standard deviations, we're getting out here in the tail, we say 830. I'll try to exaggerate that. Now, going backwards, I think we have 390. 390, the next one would be 280, 280, and also lastly 170. Dun, dun, dun. So we have our probability density function, our normal distribution. But in this instance, we're saying this normal distribution here represents the distribution of scores on the SAT if these parameters, this 500 and this 110, were accurate. So that being said, here's the deal. We wanted to find the probability that a randomly chosen individual gets a score greater than 700. And we have a nifty little table that'll help us find these probability distributions. The only problem is they use z-scores. So we need to take all these original scores and convert them to z-scores. And as a matter of fact, not all of them. These would be easy to convert. This would be +1, this would be +2, +3. We already calculated these standard deviations. So now that we've done this, we could say these scores down here are not x values, these are z values. And it's going to help us find our way around. So I'm going to switch over to pink. That way we can really exaggerate things here. But let's start with A. So the likelihood that an individual, so we'll write the probability of a score is greater than 700. So x represents our scores. We want a score greater than 700. And underneath this, we're actually going to say, well, that would be the same thing as if we converted this x value to a z-score. We want a z-score of what? So remember, a z-score is just the number of standard deviations that a datum falls above the mean and is given by this formula here. But you take the datum minus the average, and we'll divide by the standard deviation. So let's go ahead and draw on what we want. We said a score greater than 700. Well, we know 700 is just simply somewhere in here. So we say 700. We want to know this is a z-score. Z-score. So we say z 700 minus the average of 500. This is all over 110. So we end up with 110 tenths But let's go ahead and calculate this. So 200 divided by 110. I don't know if everybody can see this. 1.81 or 82-ish. So this is a positive 1.82. So I'm going to go ahead and draw in the shaded area we're trying to find here. But we want these individuals that fall up here at scores above a 700. So we want to know how many people this is here. Excuse me. So we're going to go look up in our table a z-score of 1.82 and see what it has to say. So we get, oh, wrong one. 1.82, I get 0.9656, or on most tables you get 0.4656, but really what that's telling you is with that z-score, 0.4656, that's how much area is from the mean out to that particular z-value. Now we don't want this, we just want the tail. So since half of this distribution represents 50%, we'll just say, okay, so 1.82, that was equal to 0.4656. We'll go ahead and subtract this from 50%. Minus 0.4656. So we say 0.5 minus 0.4656. Yeah, I know, I'm being lazy. But we get this. 0.0344. 0.0344. So roughly 3.44% that you'd randomly grab an individual that gets a score greater than 700. So I guess what I'm telling you people is if you get a score of 700, you should feel really good about yourself. Excuse me. So the next one, really quickly, we wanted a score between 550 and 650. I'm going to be less explicit here. We'll just go ahead and try to find this. But we say 550. Perhaps we'll switch over to green to kind of switch up which one we're doing here. So we'll do this guy in green. But 550 to 650, let's go ahead and highlight what we want. So 550 would be somewhere in here, 550. And 650, of course, would be over one standard deviation. So we need to change these to z-scores. So we have 550 minus 500, so that's positive, so we're above the average. That's cool. So that'd be 51/10. And then over here we say 650 minus the average of 150. It's 110. So we get, well, the average is not 150, sorry, 500. I'm already thinking the difference here, but you get 150 over 110. So let's go ahead and do both of these here. We've got 50 divided by 110, 50 divided by 110. Cool, 0.45. And we had 150 divided by 110. So 0.45 and 1.36 respectively. So this is 1.36 and this is 0.45. So we want to find these individuals right here. So we're going to need to find two z-scores, but actually we're going to need to find the difference of this long one and the short one. We'll just subtract off the short one. So looking these up, 0.45, 1.36. So 0.45, our smaller one, 0.4, we'll go over here, 5. It'd be 0.1736, so 0.1736, and so 1.36, 1.36, 0.4131, so 0.4131. Okay, so essentially, let's see here, 5, 0, 12, 9, 3, sorry, I haven't had to subtract this way in a while, but we say 0.2395. So, and if you look over here, I mean, that's entirely reasonable. So, but yeah, this is just a couple of examples of how you would use this standard normal distribution. Enjoy.